Okay, welcome everyone. This is a new meeting of New England Dynamics and Number Theory Seminar. And our speaker today is Michael Bersudsky from Columbus. And the title is Equidistribution of O minimal curves in homogeneous spaces. Take it away.
Yeah, thanks, Dimitri. Thanks, the organizer, for this platform. And especially thanks, Tariq, for inviting me. Okay, so I'm going to talk about this this work. It's a joint work with Nimish and Xing. Okay, so let's start. So our main objects are is a closed subgroup, a closed algebraic subgroup of SL and R. Nice example is just Rn. It's probably you all know you can always embed algebraic subgroup inside SLNR, so this is pretty general. Gamma is a lattice, so let's recall briefly what's a lattice. Discrete subgroup having a finite volume fundamental domain with respect to the Haar measure of G. So having that, G mod gamma supports G invariant probability measure. And some nice examples to keep in mind is the lattice Zn in Rn or SLNZ in SLNR. So Rn mod Zn is the torus and dimensional torus. SLNR mod SLNZ is space of lattices. So our main goal is to describe limits of averages along curves in G modulo gamma. What do I mean? So you take some unbounded curve inside the SLNR. Yeah, it's like a matrix curve. You take a point in G mod gamma and you average from 0 to. And our main result is kind of a robust statement about the rich family of curves, which is in a certain sense it's optimal. And the optimality is in the sense that those averages always converge to a nice measure, algebraic measure. It's a measure that's supported on a subtorus, you can think. Yeah, it's a kind of extension of Ratner's equidistribution theorem for one-parameter flows. By the way, if you have any question, please ask, but only questions that, of course, I can answer. Okay, so let's move on. I did a few illustrations, which I think may be nice to see. So for example, you consider the curve T squared, this polynomial curve, in R2 mod Z2. And here is an illustration how he evolves in time. We increase the parameter T, some part of the orbit, and here is a kind of other extreme case when you look on SL2R mod SL2Z. So SL2R mod SL2Z is not compact, and the behavior is different. And here I'll consider this kind of curve. It's composed of these rational functions, and here is the image in the modular surface after I quotient by SO2. So looks like that. Yeah, and what are we doing? We take some nice compactly supported function on this space and average along this curve. Okay, so now I'll recall the kind of the main motivation. It's a classical, very important theorem of Ratner from 91. It's stated as follows. So let U of T be a unipotent one-parameter subgroup. Yeah, it's a subgroup which is it's generated by exponential of nilpotent matrix, or you can think of it like, yeah, just unipotent matrices in one parameter group. And take gamma be a lattice, and you take a point in G mod gamma, then we have this really nice equidistribution statement. So those averages along the unipotent orbit always converge to a nice measure. So what is this nice measure? H, you take H, a closed connected subgroup such that this orbit is closed, and this orbit has a finite H invariant probability measure. Okay, so some generalizations of that theorem. The first one I would like to mention is of Nimish's from '96. So he considered the more general case. He took curves which are polynomial, namely, it's not necessarily a subgroup or anything, just some matrices with polynomial entries. Yeah, and he also had a higher dimensional analog there. And more recently, there is the work of Peterzil and Starchenko, and they considered the setup that G is a closed subgroup of the unipotent group, upper triangular unipotent group, and they took what we call a curve definable in a polynomially bounded O-minimal structure, such that this trajectory through this base point is dense in G mod gamma, and they show that it's equidistributed. So probably many of you or some of you are not familiar with this O-minimal notion. So this is my plan now. I just want to emphasize here that in their work, they also consider the more general thing. They considered higher dimensional sets and projected them to G mod gamma and described their closure, got like Ratner-like theorems for the closure. Okay, so in order to present O-minimality, I would like to start with the motivation of O-minimality in a sense. It's a semi-algebraic geometry. So what is the semi-algebraic geometry? First, we need to define a semi-algebraic set. So semi-algebraic set is collection of algebraic sets, namely zeros of polynomials, and also inequalities. Yeah, P here is a polynomial, and you take all of those kind of sets and you take finite Boolean combination, namely you take unions, intersections, complements in any dimension n, and those are the semi-algebraic sets. And another important definition is a semi-algebraic function. What is a semi-algebraic function? It's a function whose graph is semi-algebraic. So let's have a quick example. So here, this function is semi-algebraic. So let's, for fun, verify this according to my definition. How do you show that this is a semi-algebraic function? So I claim that the graph is the union of those two sets. Let's see. So here x is negative and y is negative, and this thing equals 0. By moving sides, you get this expression for x smaller than 0. You'll have the graph x minus square root absolute value of x. And on the right, it's kind of similar idea. Now, what's important in this that you don't really need to go through the definition. There is very nice properties. So if you take several semi-algebraic functions, you compose them, you get again semi-algebraic. if you take some injective semi-algebraic function, the inverse again semi-algebraic. If you multiply semi-algebraic functions, you get semi-algebraic. Take a ratio semi-algebraic functions or a sum. That's all semi-algebraic. So it's pretty very rich collection of functions, very flexible.
Excuse me, can I show the definition again? So semi-algebraic is when the graph is a semi-algebraic set?
Yeah.
Okay, right. Okay, so all right, I understand. Okay.
Yep. And more questions? So all minimal structures is a natural generalization of this nice geometry. In an overview, no minimal structure is a collection of certain sets, sigma n, in each dimension. And those collections are, in order to call this collection of sets O minimal, they need to satisfy certain axioms. I'll present it in the next page quickly. And those semi-algebraic sets are the smallest O minimal structure. In any O minimal structure, of course, O minimal structure expanding the real field, there's various notions of O minimal structure, but for us, O minimal structure is one that expands the real field. So always an O minimal structure has all semi-algebraic sets. So it's possibly larger. So this notion was introduced by Van den Dries in '86 in this nice paper. And
Sorry,
since then,
sub-algebraic is the same as semi-algebraic.
did I said, sorry, so it's a typo. Yeah, semi-algebraic.
Okay, well, whatever. We can
Yeah,
use
there is no two notions. Sub and semi for me the same.
Okay.
And just as a quick example, even before I defined the semi-algebraic, before I defined O minimal structures, so a larger O minimal structures also contains those semi-algebraic type sets, which also include power functions with some maybe irrational exponent, and also contains stuff that are defined by analytic functions restricted to compact sets. So it's important that we take analytic functions restricted to compact sets. For example, sets that are defined by tangents of X are also in this O minimal structure. So I don't think that now my plan is to quickly show those axioms for O minimal structure, but I don't think that they're very enlightening. I just want to give you a formal definition quickly, just to have something concrete in mind. So O minimal structure, as I said, is a family of sets in each dimension. So in each dimension, you have some collection of sets, and they need to satisfy the following. So for each n, those collection of sets is a Boolean algebra. Namely, if you take two sets, you take a union of them, it still has to be in this script Sn. If you take complement or whatever, or not whatever, complement, intersections, and unions. And Rn also has to be there. In each dimension, we need that the script S will contain diagonals. What do I mean? Diagonal is just those subsets where two coordinates are the same. Yeah, say x1 equals to x2, and the rest is something, or x3 equals to x4, and the rest is something. All of those sets have to be in script S. Cross product. So if we take A and we cross product it with R, it gives us a set in a higher dimensional script S. This is a very important one. So projection, if you have a set in n-1, n+1 dimensions, and you project to the first n coordinates, then it also has to be there in this collection. Another important thing is that in 3 dimensions, we must have the addition graph and the multiplication graph. So those properties already, you can use them to show that those script S have to contain all semi-algebraic sets. And this is a crucial requirement, is that the one-dimensional sets are precisely finite unions of points and intervals. Okay, so this is an minimal structure. And I just want to say a bit on model theory. Definitely, I'm not an expert, but I hope I can give you a feeling. So there's a more natural definition of this minimal structure, and it uses the notions of model theory, notions like languages and first-order logic formulae. And I'm just going to give a small example. So yeah, this is kind of a formula that we are all used to, I guess. And this formula defines a set. How do you take a formula and you define a set? So you see here you have condition on ABC. And what is this condition? Those ABC, you can think of them as coefficients of a quadratic polynomial which has a real root. And in addition, you require that sum of squares of plus 2 coefficients is 1. And I claim that this set is, in fact, a projection of a subalgebraic set. Why? So consider this algebraic set, right? This is just a variety, A, B, C, X, such that this combination is 0. And you project it to the first 3 coordinates. And the remarkable thing is that this is, again, subalgebraic. As we know by elementary college algebra, right? We have the discriminant formula determines a root if a real polynomial has a root or not. But so this, you can think of it like that. But this is more general, and this is those famous Tarski-Zindenberg theorem, which states that if you take any semi-algebraic set and you project it to first n coordinates, you again get a semi-algebraic set. So even if you took here some crazy polynomial and ask the same question, it will be again some finite union of inequalities or equalities of some polynomials. Okay, so some more notions on minimal structures. There is the notion of definability. So given an minimal structure, sigma, a set is called definable if it's just a short way to say that it belongs to script S. A function is said to be definable if its graph is definable, exactly like we had for semi-algebraic sets. And also, as I mentioned, for semi-algebraic sets, if you take compositions, inverses, products, ratios, and sums of definable stuff, you get definable stuff. And now we'll be focusing on curves. So what is a definable curve in a minimal structure? It will be definable if each coordinate, right? So you have a matrix phi, it's a curve of matrices. It will be definable if all coordinate functions are definable. So now my goal is to give some counterexamples for equidistribution. When do we take such a nice curve, and can we expect for failure of equidistribution? So first example is the log function. So if you take the log function, think of it as a curve in R, in the real numbers. And I'll show that those averages in R mod Z, in the circle, are failing to converge. Possibly there's many weak star limits of the measures. So to see that, let's consider this exponential function, e to the 2 pi I x. It's a function on the circle. And what I'm going to do is average this log t curve along this, I'll average this function along this curve. So what do we have? We consider this integral. And what is this expression? So this is just this monomial t to the power 2 pi I. E to the power 2 pi I log t is just t to the power 2 pi I. This is very easy to integrate. Oh, sorry. So here I forgot the exponent. It should be t to the power 2 pi I plus 1. That's the classical integral formula of a monomial. And when you divide by t, you are left with this annoying t to the power 2 pi I, which is just oscillating. Yeah, it's not converging to nothing. Okay, so this is one bad thing. So this such a logarithm expressions we would like to avoid. And there is a nice dichotomy theorem in minimal structures proved by Chris Miller, which is my neighbor in the upstairs floor. And it goes as follows. So a minimal structure is called polynomially bounded if for any definable function f of t will be smaller or equal than ct to the power n. Yeah, just bounded by a polynomial. And Chris Miller proved that a minimal structure is polynomially bounded if and only if the exponential function is not definable. So only one implication is non-trivial. Yeah. And okay, so as we said, if something is definable, then inverse will also be definable. So here, if we restrict ourselves to polynomially bounded or minimal structures, then we will not have the first counterexample. So this will be our setup from now on. Our structures are just polynomially bounded. And another counterexample is escape of mass. Sorry. So SL2R mod SL2Z is not compact, and the curve can just escape to infinity. And this is a very simple example. So this is a nice semi-algebraic curve. And as we all know, or many of us know, that it behaves it's not very rigid. So let's recall what is here the classical easy counterexample. So SL2R mod SL2Z is space of lattices. And a lattice, by Mahler's criterion, a lattice is close to infinity if it has a very short vector. So here, if we'll take Z2, the lattice Z2, and apply this curve to it, it will shrink a vector clearly. And so this will escape to infinity directly. And so the measure will just converge to 0. More generally, if we take a curve in SLNR, and if there exists a tuple of linearly independent vectors, such that this exterior product converges to 0, then there will be a lattice, n-dimensional lattice, which converges to infinity. So here, what does that mean? It means that this is the exterior product. What you can think of it as this curve will be shrinking a parallelogram determined by these vectors. The lattice will degenerate due to that fact. Okay. So now we'll also like to avoid that counterexample. And those will be the only ones. Yeah, those two natural counterexamples will be the only bad examples in our theorem. So to avoid the previous counterexample, we want to avoid this contraction in a finite dimensional rational representation. So we say that the curve is non-contracting if for every finite dimensional rational representation, it holds that the curve does not shrink non-zero vectors to 0. And okay, so this may look like a very difficult thing to verify, but let's have some examples, and I hope to convince you that it's actually very verifiable and can be in explicit examples. It's just an exercise. So first, if you take curve phi, which is contained in a unipotent group, then phi will be always non-contracting. And the reason for that is that this well-known fact that every orbit of a unipotent group in finite dimensional representation is closed. So if you take a vector which is non-zero, it cannot contain 0 because the orbit of 0 is 0. And now I'll give you a quick verifiable condition for non-contraction. So instead of considering all possible representations, it's enough to consider those exterior products. This is the main statement. So if we take a group G, which is generated by unipotent one-parameter subgroups, for example, G is some simple group, and the curve is, say, continuous and definable in a no-minimal structure, then the curve will be non-contracting if and only if it will not contract vectors in this exterior product. And this is something that you can verify. It's kind of, you write the expressions, you take some basis of this vector space, and then you can represent this matrix in this vector space. And you can see, according to the functions, if it will shrink a vector or not. So this statement, just quickly, it's based on this Kemp's fork and this tools developed by Nimish and Pengyu. Okay. Okay. Now we arrive to our main result. So here we suppose that we take a curve is continuous, unbounded, and definable in a polynomially bounded O-minimal structure. Then, so first thing which took us time to prove is that there exists a certain unique subgroup, which we call it the hull. I don't have time to really describe it, but it has some very nice properties. It just depends on the curve. And this group is generated by one-parameter unipotent subgroups. And our curve is not necessarily contained in this group, but it's in a bounded distance from this group. And moreover, we can correct the curve to be in this group. So, namely, there exists a bounded definable curve such that if we multiply our curve phi of t, this new curve will be contained in H phi. Okay, very good. Now the statement will be as follows. So you take a lattice in G, and you take a base point, G mod gamma, and you average along the curve, and the measure, those measures will converge to an algebraic measure. Now, what is this L and what is beta infinity? I will now explain. So first thing, as I said, H phi is generated by one parameter unipotent subgroups. And Ratner's measure classification theorem states that the closure of H phi passing through X naught is an orbit of another group, possibly larger, which has an invariant measure. Yeah. Is there a question?
I think somebody's microphone was just unmuted.
Okay. Okay, and what is this beta infinity? So maybe a simpler picture to have in mind. So if you correct this curve to be in H phi, so this curve will be equidistributed in this L. But reversing back, you just need to, so this curve will converge to something. Every bounded thing in no minimal structure, every bounded functions always converges. So this will converge. And by doing here, it should be beta infinity, sorry. So by taking the inverse, you get the limit of the original average. So in a sense, it will converge kind of asymptotically to this periodic orbit L, to this subtorus Lx naught. And here is my favorite example. I think it's ours. So we have this this curve, very kind of simple, nice curve. So it's a curve in SLN plus 1 and has some conditions on those degrees. Yeah, it can be real numbers, not necessarily fractions or not necessarily polynomial. There is some condition. The important thing about this curve is that every vector that you take in an exterior product of Rk, it would go to infinity. Yeah, it takes every vector to infinity. This is the condition here. Then the statement is that for every lattice gamma and every base point in SLN plus 1 R mod gamma, it will always equidistribute towards the measure on G mod gamma. Yeah, it's like you have this high dimensional space, SLN plus 1R, and you have this one dimensional curve, and it avoids all of the possible bad restrictions, always equidistribute for every lattice, for every base point. And the idea to prove this, so we just need to show that this group H phi is the full group SLN plus 1R, and this uses those tools developed by Nimish and Pengyu. Okay. So now I'll move to talk about proof ideas. So the proof structure is kind of something that became very basic in homogeneous dynamics. It also appeared in Ratner's proof of her equidistribution theorem. So the idea is as follows. So you take a limiting measure of this of those averages on curves. And the first thing to prove that the limiting measure is a probability measure. Of course, it's trivial if gamma is co-compact, but otherwise it's not very easy, not always easy. Second thing is to show that the measure nu is invariant under unipotence. So once you have that the measure is invariant under unipotence, you can apply Ratner's measure classification theorem for ergodic components. So every U invariant and ergodic is algebraic. And then the goal is to study this ergodic decomposition of nu by studying representations. Standard technique is this Dani-Margulis linearization technique. So the interesting thing is that first, that those curves, when you average on them, they pick up some direction in a sense. If you think about it geometrically, for example, if you think of the curve t comma t squared, it becomes more like asymptotic to the vertical direction. So the measure will be invariant at least under vertical translations, and it's kind of the general phenomena. There is some phenomena of tangency at infinity. I'll talk about this if there's time. And to show that there is that this probability measure, and to apply this linearization technique, we need to have some good control over sub-level sets of linear combinations of O minimal functions, and this was something that we worked hard on this. Okay. So regarding this control of sub-level sets, we would like to recall the classical Kleinbock-Margulis C alpha good property, which is a particular very useful in studying Diophantine approximation. And I'll just consider a one-dimensional version. Of course, it's done for higher dimensions. Okay, so what is the C alpha good property? Sorry. So suppose you take an open set and the function on the open set, say some interval, and you say that the function is C alpha good if for all subintervals and epsilon bigger than 0, you have this control over the length of the points in which the function spans below epsilon. So it should be at most C times epsilon to the power of alpha. Why is this why is this property is useful to show, for example, that the limiting measure is probability? So I'll just say quickly, if you think of SL2R mod SL2Z, so a lattice will be very high at the cusp, very close to infinity if it has a short vector. So you want to control the time that the vector is short. And this is exactly the thing that we need. So what is known about this property? So many things are known. And there is the following well-known result in the 98 paper of Kleinbock and Margulis. It's stated as follows. So if you take L times differentiable functions, and you take a point in the interval such that those vectors composed of jth derivatives from 0 up to L, they span Rn. So then there exists a C such that all linear combinations are C1 over L good in J. And this is important here. So J is some sub-interval. It's not that the linear combinations are C alpha good in whole I. They're C alpha good in J. And this was the main reason we couldn't apply this theorem for our case, because we have functions on array from 0 to infinity, and we want this C alpha good property on the ray. We cannot have a small subinterval. It's not enough. So I'll just say that this property on such domains appeared in Dani-Margulis, but it's also something very classical in analysis. It's called Remez inequality, and this C and alpha are optimal, I guess. Okay, so our goal is to, my goal now is to present the C alpha good on rays. This is the thing that we needed. So we take a vector space, a finite dimensional vector space spanned by functions. So it's just all linear combinations of finite family of functions. And we take those functions to be definable in a polynomially bounded or minimal structure. Now, inside of here, you might have functions that decay to zero. So what we are doing, we take a subfamily of functions f, which is a definable cone. What does it mean? It means that if you multiply the functions by scalar, then you're still there in f. So f is some cone. It's not necessarily a subspace or anything like it. And the requirement about this cone is that any non-zero function doesn't converge to zero. Then we get a C alpha good property for the cone. Namely, there exists a C alpha and T naught positive, such that for all functions, all non-zero functions in the cone, restriction of this function on this T naught infinity interval is C alpha good. Yeah, we don't care about the range from 0 to T naught, because when we average and normalize, we kill this integration up to T naught. So it's okay for us. And this T naught doesn't depend on C and alpha. So for me, it was kind of surprising that it was not, as far as I checked, it was not even known for such linear combinations. I don't know if it's very difficult or just nobody really was into it, but I think it's really kind of nice, delicate property in this nice collection of functions. So, yeah. So how do we use this theorem? So we use it as follows. So you take this curve, definable curve in a polynomially bounded or minimal structure. You take some rational representation. Then this norm will be C alpha. Yeah. When you take those collection of norms, you get this cone, because if you scale, you're still in this collection. So, and this, because this is non-contracting, this condition will be satisfied. Okay, so now I would like to give some ideas for this this property. So we use it in this linearization technique, and also to show that there is no escape of mass, that always the averages converge to probability measures. And how do we prove this alpha a good property? So the first thing is to state a different statement which will imply the C alpha good, which will be more convenient to use with this O minimal structures theory. So instead of C alpha good, I'm going to consider delta good. So what is the delta good? A family of functions on this array, T naught infinity, is called delta good for some delta in 0, 1, if there exists a constant such that these ratios of supremums of the functions on the interval and on the subinterval is at most m delta. And this m delta, this inequality should hold for all possible functions and for all nested intervals which have a relative length at least delta. Yeah, so you can imagine that you can take the function possibly has some 0, and this supremum might be small, and this supremum shouldn't be too large then. Yeah, it should grow in a controllable way in a uniform manner like this. So to prove this, for example, in Margulis, they proved it using interpolation. But here in our setup, it's not possible to use interpolation, although I spend a lot of time on that and kind of, yeah. So the idea will be the same. It will be different idea, not use interpolation like Margulis. So here is our statement about this delta good. So the setup is the same as before. We have those polynomially bounded or minimal functions, and we take a cone. So then there exists a T-naught such that all of these functions, I should say non-zero functions, restricted to the ray are delta good for every delta between 0 to 1. Okay, so now I want to do two things. First is to give you an idea of how this is proven, and how will this imply the C alpha good property. So first thing is to show you why, at least give you an idea why delta good implies C alpha good. And I'm also telling you this because this is kind of the main tool we use from all minimal structures. It's called the choice function theorem. And I think it appears in many different other works. So it's stated as follows. So if A is a definable subset, and you take then you have a definable function. It's called the choice function from the projection of A to the first coordinates to A. Okay, so here is the nice thing. So if you consider this set, it's a set in R2, and the condition on this delta M is just something that involves definable stuff using first order logic operations. So this set is definable in our polynomially bounded or minimal structure. For example, if the structure is just semi-algebraic sets, then this delta M pairs are the semi-algebraic. Now, by our theorem, we always, for each delta, we have an M. So the projection is 0, 1. And we get a choice function. So we can choose this M using delta. And this function is definable function in a polynomially bounded or minimal structure. So we get that this M delta is at most some constant times delta to the power of R. I think it should be 1 over, yeah, if delta is very small, so it should be, R negative here. And using this control, then we can prove the C alpha good property. One important thing in the next step is to use the fact that every O minimal function has finitely many connected components. Moreover, all of those linear combinations have uniformly finitely many connected components. Okay. The next thing is to give you an idea of how to prove delta good property. So the idea is as follows. So fix some delta, and assume for contradiction that for all, so let's assume for contradiction that C alpha, that this delta good property it doesn't hold. Then what does it mean? It means that for every S bigger than 0, those supremums will be at least S for some intervals which have relative length delta, and there will be some functions satisfying this inequality. So using this will be a definable condition, and using this again, using choice function theorem, we can parameterize those counterexamples using, if we are working in semi-algebraic sets, so this will be semi-algebraic parameterizations, namely those, right? So we have the function is in a finite dimensional vector space, so the coefficients will be some functions depending on S, which you can control very nicely, and those intervals will also, their endpoints will also be controlled in a nice way. And then there is some kind of delicate analysis that we break the counterexamples into different cases. And each time using this control, we get a contradiction. That's kind of, in a sense, okay. Yeah. So that was the idea for C alpha good property. And now I'll move on to the last part, tangency at infinity. How to get unipotent invariance. So why am I calling this tangency to infinity? So here we have a difference of curves, and ht here is a function that goes to infinity in the speed of t. Yeah, and its derivative will be converging to 1. And the interesting fact is that when you take this difference, it will converge to something. And in our case, it will always converge to a unipotent element. So you can imagine the curve t comma t squared, which I'll write in a second. So why would this give invariance? So let's see step by step. So we would like to show that this limit, if we take a left translation of our function, the average in the limit will not change. It will be the same. So here I'll be taking u, which is obtained in this manner. Yeah, so I have f of u times phi t, left translation of the function. Now u is simply obtained as the limit of those expressions. So using uniform compactness, uniform continuity, sorry. Uniform continuity, those right-hand side and left-hand side are the same. And then you see this phi of t cancels, and instead we get phi of h of t. But now substituting a variable using this fact that the derivative is essentially a constant, we get the original integral. Yeah, so the average along left translation is the same as the original average. So let's see how it works, for example, for this curve, right? So here, the tangent at infinity will be just the perpendicular, the vertical vector. So here is our change of speed map, h of t, t plus 1 over t. So let's take a difference, right? So here is the additive group. So we have phi of h of t minus phi of t. What do we get? So in the first coordinate, it's just 1 over t. In the second coordinate, after you take a square and subtract, you're left with 2 plus 1 over t squared. So this converges to 0. Yeah, so this average that we saw along t squared at the beginning of the talk will be invariant under the vertical direction. So this idea appeared already in Nimish's work, and interestingly, it was generalized to O-minimal setup, and the interest there was something related to O-minimal geometry, not related to equidistribution. I'm not sure that they knew about Nimish's work back then, but yeah, I'm not sure. But it seems used a completely independent interest. But in the recent work of Peterzil and Starchenko in those nil manifolds, they did use this idea to get invariance of the measure. So this criteria, to get those functions in the polynomially bounded case, it was studied by Starchenko's student, and he provided a very convenient criterion for when do we get a unipotent invariance using this tangency in infinity. So here is the main statement that we use. So consider a curve in SLNR, unbounded and definable in a polynomially bounded or minimal structure. Then there exists a unique R such that a limit of t to the power r times this. So this is just the coordinate-wise derivative. This is an element in the Lie algebra. In the Lie algebra of G, so there exists a unique R such that this converges to a matrix, which we call M phi. This matrix will be nilpotent if and only if R is smaller than 1. Otherwise, this matrix is diagonalizable. Now, moreover, if R is smaller than 1, we provide the explicit family of change of speed maps, and we get a one parameter unipotent subgroup. It will be the exponential of this nilpotent matrix, and this exponential of this nilpotent matrix is exactly the limits of those differences at infinity. Yeah, so those curves, if you take your curve, you differentiate coordinate-wise, you consider this matrix expression, you find this R. If this R is smaller than 1, then you have unipotent invariance when you average along the curve. And our goal was to use this criterion. We had to verify that if we take a non-contracting curve, then necessarily R will be smaller than 1. And the difficult thing was to kind of work with this derivatives, and we came up with some nice notion of essentially diagonal, and when it's not contracting, it cannot be essentially diagonal, so we get unipotent invariance when we take a non-contracting curve. And I guess I'm going to finish early, so I just want to say the last thing. So this condition, the non-contraction, is not necessary. You can have contracting curves for which you still get unipotent invariance. So let's do this nice exercise. So we have this upper triangular curve. Yeah, here the domain is t at least 1. And we take alpha exponent to be at least -1. It can be negative. This is the point. So if the exponent is negative, then this curve can contract a vector. For example, if you apply it on the vector 0, 1 on the y-axis. So it can contract. And I claim that if the R is minus alpha. So if alpha, yeah, it means that R is smaller than 1. And the expressions that you get after you take derivative is just this thing, and this will converge to 1 minus alpha, which is clearly nilpotent. So this, if you average along this curve, even though say alpha is -1/2, so here you have 1 over square root t, this curve will still give unipotent invariance. And the interesting thing is that if you take a co-compact lattice, then this curve will equidistribute, since the unipotent group is uniquely ergodic in this case when gamma is co-compact. Yeah, so that's all. I'm happy if you have any questions.
Okay, so let's have a round of applause for Michael's talk. Any questions? Indeed. So can you just probably said it before, but I'm not sure. So you get self a good property and use self a good property to get non-escape of mass.
Yeah.
For the curve, but then for equidistribution you're using it too.
Yeah.
Get
you need to control, right? So for example,
so you're going through this linearization.
Yeah, exactly. Yeah, this is exactly what this alpha good, as I stated, is exactly what we need for linearization.
Okay, yeah, very nice. Maybe just a wild question. Everything is restricted to curves, but if you want to have a R2 map, then does these things do these
Yeah,
things?
we started thinking about it. So, for example, we started thinking, like, say you take a cone in R3, take a cone and project it to those.
Yes.
It seems like it should be equidistributed. So every direction, right? It's composed of lines. Most directions are irrational. You can fiber it. Something. Yeah, I mean, we have some ideas, but it's could work, but not really. Yeah, so C alpha good property we couldn't do yet.
So it's not known if this projection of the cone is equidistributed.
I don't think it's written anywhere. I don't think also it's very, like if you take a ball, intersect it with the cone, you can fiber the cone. Most directions will be, almost every direction is
Yes.
irrational, I guess. Yeah, I don't want to risk it, but I mean, this kind of ideas, when Nimish did the polynomial curve, he fibered the higher dimensional sets using one dimension.
Okay. So if you
That's
can do it,
some idea. Yeah. Maybe there is a better way to do it, but yeah, we don't have concrete.
I see. Yeah. Well, a natural approach is to fiber by curves, but also maybe
Yeah, maybe it's something more intrinsic.
but there is no such thing as O minimal surfaces.
There are, yeah, there is, and this is a natural research direction, because Peterzil and Starchenko, one of the motivating works here, is they did it for higher dimensional sets in the nilpotent case.
Mm-hmm.
They take unipotent group, they take not even polynomially bounded, they just take set definable in an O minimal structure, project it modulo gamma, and look on the closure, not equidistribution. And they get like Ratner-like kind of thing.
Mhm.
Yeah, so it's a question, like you take such a nice semi-algebraic set in SLNR, you project modulo gamma. What is the closure in G mod gamma?
Mhm.
Not known.
I see. Other questions? Okay, I seem to be the only one asking questions, so let's let me shut up. Thank Michael again for a great talk. Thank you.
Okay.
Thanks.
And we'll come back next week for something interesting. So
Yeah, it was really nice.